Welcome to Insertion Sort. Insertion Sort builds the sorted array one element at a time. It takes each element, called the key, and shifts sorted elements to the right, until it finds the correct position for the key. Then it inserts the key into that gap. This is similar to how you might sort a hand of playing cards. Insertion Sort is very efficient on nearly sorted data. Let's watch it in action. Starting pass 1. Comparing 68 and 78. 68 is not greater, no swap needed. Starting pass 2. Comparing 78 and 7. 78 is greater than 7, so we swap. Swapped elements at positions 1 and 2. Comparing 68 and 7. 68 is greater than 7, so we swap. Swapped elements at positions 0 and 1. Starting pass 3. Comparing 78 and 20. 78 is greater than 20, so we swap. Swapped elements at positions 2 and 3. Comparing 68 and 20. 68 is greater than 20, so we swap. Swapped elements at positions 1 and 2. Comparing 7 and 20. 7 is not greater, no swap needed. Starting pass 4. Comparing 78 and 21. 78 is greater than 21, so we swap. Swapped elements at positions 3 and 4. Comparing 68 and 21. 68 is greater than 21, so we swap. Swapped elements at positions 2 and 3. Comparing 20 and 21. 20 is not greater, no swap needed. 5 elements are now sorted. Congratulations! You have successfully completed the insertion sort lesson. Let's review what happened. The algorithm sorted the array in 4 passes. It made 9 comparisons each time it compared the key element against the sorted elements to its left. It performed 6 swaps, each shift moved the key 1 step left toward its correct position. The original array was 68, 78, 7, 20, 21. After sorting, the array became 7, 20, 21, 68, 78. Here are the key takeaways from this lesson. First, insertion sort picks each element as a key and shifts it left through the sorted region until it reaches its correct position. Second, after each pass the sorted subarray at the front grows by 1, and the key element is placed into its exact correct position within it. Third, in the worst case, the time complexity is order n squared. This happens when the array is sorted in reverse order. Fourth, the space complexity is order 1. Insertion sort is an in-place algorithm that uses only a constant number of variables, no extra memory is needed. Interesting insight, 6 swaps out of a maximum of 10 a typical average case run. Now let's explore the time and space complexity of insertion sort in detail. Best case O, n. When the array is already sorted, each key element needs only 1 comparison and 0 shifts. The inner loop never runs. The outer loop still iterates n-1 times, giving linear time. Average case order n squared. For a random array, the key shifts about halfway through the sorted region on average, giving roughly n squared over 4 comparisons and n squared over 4 shifts. Worst case order n squared. When the array is reverse sorted, every key must shift all the way to index 0. This produces 1 plus 2 plus ... plus n-1, that is n times n-1 over 2 comparisons and shifts. Space complexity order 1. Insertion sort is an in-place sorting algorithm. It only needs a few temporary variables regardless of the input size. No auxiliary arrays are created. When should you use insertion sort? Insertion sort is the algorithm of choice for small arrays and nearly sorted data, where its inner loop barely runs. It is also used as the base case inside hybrid sorts like timsort and introsort for subarrays below a size threshold. When should you avoid insertion sort? Avoid insertion sort for large, random datasets above a few hundred elements, where its order n squared worst case becomes a bottleneck. For large inputs, prefer merge sort, quick sort, or timsort. That's everything about insertion sort. Well done on completing this lesson.